Hi, everyone. So I'm here with Jikun Kang to discuss his paper, Think Before You Act, Decision Transformers in Working Memory. Jikun has a PhD from McGill University and Mila. He's published work in top-tier conferences and holds over 10 AI patents. And he currently is a founding research scientist at Convergence AI Labs. I'd like to start by saying congratulations on the new role at Convergence AI. Are you able to share anything about what you're working on?
Some posts have been reviewed. We're working on something called large meta-learning model. So this is something beyond the current LLM. We want to make something more smarter, more efficient, and more and we will and more safety of course. So we're targeting these directions, and yeah, hopefully we can make some progress and announce to everyone in the future.
Can you tell us just a little bit about your journey to machine learning in general, but also this reinforcement learning space?
So I started my PhD around 2017, but I already very familiar with this machine learning and reinforcement learning starting from 2014. Or late of 2014 or early of 2015, there was a big news, which is AlphaGo. Like the first time we saw challenges from the human side, but from the robotic side, from the computer, from the neural top tier Go players in this very complex Go, like even like some humans cannot be able to play it. And we thought it's played very well. And then I started to like focus on it and have very interested in this area. And I read the book about reinforcement learning and introduction from Professor Richard Sutton. And for machine learning at that time, my personal humble understanding was just statistics probably, and you learn class. More learning is have a grounded theory about it that you learn from exploration, and it's basically like dynamic programming. You explore the world, your space, but with a very wisely chosen. So I started this, and I think it's really interesting. Further study in my PhD to this.
In this paper, you talk about how you leverage short-term memory, kind of the way, mimicking the way our brains work with, storing something in working memory to be leveraged later on. How is that different than reinforcement learning?
I think there's not too like direct connections between these two things. Um, I would say the reason I'm adding memory because when I so the story is like there was this is actually a project between our lab and some mentors at Microsoft Research Montreal. We were at that time we were trying to build a foundation model for RL, which is really fascinating because we have a foundation model for vision tasks, we have foundation model for NLP tasks, but we don't have a foundation model for RL. We're really and we were trying to have some large data, which is coming from Microsoft, probably the playing game, reading this information, some privacy. So we have using some public data. And also at the same time, we are facing a very challenging issue about resources we have. So I started to think about myself to what circumstances I can work on. And the interesting part is when I dive into the transformer architecture, I found this quite interesting that because in reinforcement learning, you have a replay buffer. You have something you can learn from your past experience. This is quite interesting because what you learn from past will probably will help you improve your future. This is more like the Markovian properties that you make your decisions on your current states, but these states can be a stack of options. So this or past experiences or replay buffer not actually has been using or been talking into the transformer. I was trying to slightly adding this, tweak the transformer module, add a small piece of it like memory, add another operation of it, and trying to see how it goes. And that leads to this project. Memorize information as we do in reinforcement learning, this replay buffer. And I think more likely like how human will learn things from their past experience.
And just to expand on that a little bit more, I think you touched a little bit, but so what's the problem that's being solved in this paper? How does what you're doing improve or compare to existing methods?
Right. So we're trying to solving actually one problem with two benefits. The problem itself is memorization. So traditional transformer trying to memorize everything into the parameters and with them make the predictions. For example, the next token predictions, or in the decision transformer, you're making the actions. It basically depends on your past tokens. And these tokens as a Markov decision process, the past tokens is like your observation, and you stack them into your states, and you believe you're make that predictions based. This is what transformer is doing. But what we want to do here is not only we look into our past tokens, not only we'll check what has been taken so far, we want to use a memory to help us trigger some information we remember before, or some experience or some useful things we learned before, to add them together and use this chunk of tokens or information to predict the data, to predict the future actions or tokens. So I guess that's the two main differences in here. The problem we want to solve is memorization. And two benefits I'm going to talk about. One is generalizability. I found that this is particularly into the make some decision in certain tasks. Probably these tasks come from the same distribution and they share some like common things. For example, in Atari games, you always like play Joy-Cons with some buttons, and if you play by learning thing you learn from to on your current, it will improve your generalizability. Your model can be more generalized to the unseen games, to the unseen tasks, but it should be coming from the same distribution, as I mentioned in this paper. And the second benefit, so I want this memory module not only be generalizable, but also can be adaptable to new tasks. If it's enough, you will play like okay-ish into the new task, but probably not what we want. We want something more. We want something higher, and that's what you want. Adaptability. You tweak a little bit, and you want to see if the performance will gain a bit. And that's how this memory module capture things. Because from this past like few short examples, your memory modules capture the common things, capture the information it could learn from these experiences, and utilize this information in your
Okay, so these
studies
are
paper.
taking, for example, this all of the subtasks need to complete a particular larger task, and we can remember those subtasks and then store them so that we can apply them to a similar situation. In the training, how do you make sure that they're generalized enough, the things that you're storing, and not so task specific?
To make sure some distribution. When we I think the one trick is we each time we train the model, we shuffle the data from different tasks. Make sure every batch of the training tasks trajectory or sequence different tasks. The thing is when we're trying to understand this memory, which we show in the appendix to visualize the module, we actually found that okay, the interesting part is because we have some method like cross attention to make sure you gathering the information that's similar into the certain area of your memory places, and this kind of mechanism makes sure you keep and when we check them, we found interestingly you probably have some information for the task specific, but you also have some certain common knowledge you learn that will a same like a memory
Okay.
place.
Can you give us a little bit of an overview of your approach in terms of the design of, in particular, the memory module? And also, if you wouldn't mind starting with who should read this paper.
Memory module into a decision transformer, or furtherly, I believe it could be applied to normal transformer architectures like decoding only transform. The memory module what we're trying to do is to memorize these things, memorizing the common information or the meta information across tasks, useful for your better generalization and adaptability. So we tested it into different games and also robotics tasks. Can efficiently improve the training time, the generalization. I recommend I thing by or read by the readers who are interested in LLM, transformer architecture, or even agents, because I believe memory of part of what makes human human. You probably extracting only the golden memories from your past and use that memories to help you shape yourself and make yourself more like adaptable to the world, probably, or generalized to the world. And I think this is an interesting topic. I'm not mentioning this paper there's a right direction or the right approach, but I think memory is interesting topic. And I think that I've read a couple of papers of current model memories or things, like especially LLM agents with memories. I believe that will be more into a retrieval augmented generation, like RAG type. If we analogy this thing to the human, it's like I think this huge database you build for RAG, right? People can all or the because always if you have a specific question you don't remember correctly, you can go to this certain tools to help them to refresh your memory or help you to understand things. But with human, explicitly we have our own memory, something was stored not clearly or not clearly to me how to understand them, but this kind of information will help you trigger your actions probably, like causal things. So I memory module that inside of transformer, it's a representation based or vector based memory.
And then how did DTMem perform compared to the baselines that you used?
So we tested our performance in two general tasks. First, the games. So we have tried on 17. We pre-trained our model on 17 to tested tested this generalizability into four on single and check its adaptabilities in another. First, we can achieve the similar performance as baseline, which is multi-game decision transformer, normal games. We can achieve this by reducing our memory size. So a shock or 40 million parameters can compare to 2 million parameters of MDT, which is only a quarter of it. Because we have limited parameter size, so we have and also when we adapt our model into different tasks, we also found because for the few shot examples, you only have to tweak your model a little bit. If you post training your MDT or other transformer architectures, that this few shot example may not in like shifting your model distributions and shifting their actions. But in DTMem, since we capture this memories explicitly, and this memory is compact, so what you in this certain few shot examples actually plays a lot, and help you adapt more into a new. And that's I remember we around 10%.
All right, and you
Yeah.
detail the empirical results in the paper, which is linked in the description. Now, were there any limitations of the study or trade-offs that you had to make?
So I think this memory operation, the choices of memory operation is various. We only the idea of neural Turing machine. We do this with the updating for the memories and also the retrieving from memories. But we believe there are more a couple of different areas or operation choices we could make. So because we want to test if this works, but we didn't thoroughly try different or mechanism. Try what we empirically show this memory size scaling, but like do we want it really large or do we want to have some equations between this size of your memory and size of your parameters, model parameters, and also as I said, this is more for the reinforcement. The beautiful things from reinforcement learning is when you make decisions, um, the past experience will help you a bit. But for the normal transformer architectures, I do visualize improvement on myself, but it's not paper. But I do, and I also believe there's more to.
Correct me if I'm wrong. So this is focused on offline reinforcement learning. So how well do you think that this could, or this concept anyway, could work in other reinforcement learning settings?
Yeah, this specific paper. The reason I'm focusing on this is interesting. So with Scott Fujimoto, who is the author of TD3, very famous art. So the online decision transformer, I've tried my personally TD to as a loss function and to try to learn the model exactly through the interactions with the world. But this is actually cost a lot because imagine you want to learn a GPT model like if you want to build this online in online fashion, how many interactions you should like inter to play with this robot or this agent, that would be a lot. But of enough freedom to help you to actually like pre-train your model to learn something first, to have some basic knowledge of how to perform actions or how the understanding of your background or environments, that will shape you. If this method can be transferred to online fashion, but I would be more cautious to first portray this model into the offline fashion. Then maybe we do the fine tuning in the online version. And there's a bunch of online decision transfer method that already published for this paper.
And so how do you see the concept of working memory in AIML evolving over the coming years?
New works coming out, even myself, like or even like GPT-01 Strawberry project. For me, I think this kind of reflection or like react or rethinking steps are all like working memories, because more specifically, I think this is a system two approach. So the system one, let me clarify, is when you give an input to your model, you directly output it, what we does before. But system two, the current models or this kind of thinking models, is more like give the input, you do something internally inside of models, planning, thinking, reactions, build a tree of your thinking, search it, and you made output. This kind of things is more like it's system two, that you think before you
Right.
act. Exactly this paper. So this kind of things I all think about them as a working memory, because your internal thinking, your internal reflection, or generation of this tree of thoughts, um, it's basically you're generating a working memory. Each time you memorize your thinking and improve upon or trace back, then you give your final output. After this final output, you just delete all of these memories or discard them. So I do believe our current machine learning or AI is evolving in this area, but we have different, or I believe there's another fruit from the tree that is vector-based or representation-based memory that we could discover for this system two or working
Can you
memory approach.
explain that a little more? What do you mean by that?
Right. So for the current method, for example, for reflection, that you're trying to ask your model to probably answer complex math problem. And this math problem normally involves some operations, like steps probably. And this 10 steps operations actually needs you to correct them if one of these steps is wrong. And the way of doing this is you go back to your model, query the similar things by like adding maybe, do I do things correct? How do you think about it? What should I improve? And next time you generate something new and you pen them into your current thought, chain of thought or tree of thought. And after this, you build your final answer between this chain of thought or tree of thought. And this chain or tree is basically your memory for this, the token level memory for this internal thinking. It's probably like step one, step two, step three, step four, step five. till step 10. But the final, the questioner only care about your final answer. You will not let them know what happens internally. You don't won't let them know what you're thinking, but you will give a correct answer. So after giving this correct answer, you discard all of your thinking from step 1 to step 10. And this step 1 to step 10 is basically your internal memory, but it's token level. What I'm doing in this paper is I'm thinking about this internal thing, not exactly the copy of it, but analogies to representation or vector-based memory that instead of explicitly can be transferred into human readable, this is something that you add to your attention model to shift in your how you predict the next token. For example, when you make this internal steps, when making this internal thinkings, there's memory component that is trying to shifting your distribution of your token generation by adding the bias, by adding or the memory into your input to your attention mechanism, and this will finally change your behavior. And this is the way our working memory is changing the final output. But all of this are unseen to human, unseen
Right.
to your users. Yeah.
What I'm wondering with, even though you don't necessarily discuss it in this paper, but what I'm wondering, is that your goal in designing these systems, is to get them to behave more human-like?
I think that's all. I think that's the dream of all AI researchers. I remember the professor Joshua Benjo. He is a professor in Mila and one of the great researchers in AI community. He mentioned one thing for his research. One time in a topic in a speech, he was say, okay, there's a lot of students or researchers come to him and ask like how you do the research, how Professor Joshua do the research, and the answer is every time he wakes up, he was thinking about something like what human do and what current neural network doesn't do. I think that's a perfect way of thinking about your topic or thinking about your research or doing things. That's making connections, analogies between how we ourselves do things compared to current neural network models. And I think that's part of the reason I dive into this paper, build this method, and part of reason how I'm gonna research for the
Okay.
future.
So we talked mostly about the paper, but what, any exciting things coming up for you, except papers coming out? What do we have to look forward to?
I think the next exciting or part of milestone for me is I will build this what we call large meta learning model, and this will be totally different than the current LAM, and we believe this will be more human-like or more intelligent than the current model.
All right, great. If you have questions for about anything we discussed today or for Jikun, I encourage you to post them in the comments.